Okay, let's do the extra practice problems for Chapter 5. Number 1, draw the Lewis structures for the following molecules. So we go CF4. So first you find carbon. You go over here, carbon is in group 4, so it has 4 valence electrons. 1, 2, 3, 4. And then we have 4 fluorine. And they're in group 7 over here. So they're going to have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then you're going to connect the dots if it's possible. Remember, you want everybody to have, except for hydrogen, which will only have 2, but everybody else that's not one of these really tiny little guys will be trying to get a full valence. So everybody wants to have 4 pairs around them. And in this way, we actually can do that because we have carbon is attached to each of these. I'm just rewriting what we just did. And that's how we would rewrite that. And please notice everybody has 4 pairs around them. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So that's how you can check and make sure what you're doing is correct. Very important. The next one is PHCl2. Remember, as we do this, I'm on page 133. We start, number 1, with the atom with the most unpaired electrons, and we put it in the center. Then we try to attach all the other atoms to it, sharing their unpaired electrons with one of the unpaired electrons on the central atom. And then lastly, if you don't have everybody where they have their ideal electron configuration, you're going to try moving unpaired electrons in between various atoms to make double and triple bonds. So there were the simplified directions in a nutshell. So let's see, we have phosphorus over here, which is in group 5. So phosphorus has 1, 2, 3, 4, 5. Hydrogen we know has 1. Chlorine is down here, and so it's got 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, this is going to connect, and here we're going to connect, and here we're going to connect. Wow, that worked out. So let's rewrite that. The phosphorus is in the middle. Hydrogen is over here. I'm so sorry, that's a chlorine. Chlorine is here. So phosphorus has 1, 2, 3, 4. Hydrogen has 1 pair. Phosphorus has 4 pairs. Chlorine, 1, 2, 3, 4. Chlorine, 1, 2, 3, 4. So this way everybody is satisfied. So this would be its Lewis structure. Remember, you can manipulate this. You could have the chlorine here and the hydrogen here. That doesn't matter. The next one is TeI2. Te, tellurium, is right there. And it is in group 6. So we're going to go 1, 2, 3, 4, 5, 6. Iodine is all the way here in group 7. So we have 2 of those. So we have 1, 2, 3, 4, 5, 6, 7. And I cheated a little. I didn't put it up top. But when you're doing this, you're allowed to do that. So it's not cheating. 1, 2, 3, 4, 5, 6, 7. We have an unpaired pair there and 1 here. So when we rewrite this, like that. The next one is selenium, which is down here, and it's in group 6. So, and there's 2 of them. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we can go like this and go like this. Now once again, you can put these dots here and these dots here. That doesn't really matter so much, but everybody should have 4 pairs around them and a double bond between the 2 of them, holding them together. CIP. So carbon is 1, 2, 3, 4. Iodine is 7. We already dealt with that, so I'm going to put it over here. 1, 2, 3, 4, 5, 6, 7. It's one of those. And phosphorus is right here. It's in group 5, so it's going to have 5. 1, 2, 3, 4, 5. And I put this in the middle because carbon having 4 unpaired electrons, it's got the most unpaired, so I stuck it in the middle. All right, then I'm going to start connecting the dots. So I'm going to go like this. But we still have one over here, don't we? So let's see. We can go like this, and we actually could go like that, couldn't we? Let's see if that works. 1, 2, 3. Okay, and you can't gain electrons and you can't lose electrons. Matter is neither created nor destroyed, it can only change form. So we have 1, 2, 3, 4 here. You have 1, 2, 3, 4 for carbon, and you have 1, 2, 3, 4 for phosphorus. So that worked. Very good. Oh, and these guys can be flip-flop, but they just have to have the right number of bonds between them so that everybody, in other words, you could have written this, and you could have your dots there or there or there, it doesn't matter. And then, okay. Number 2, determine the shape and draw a stick figure for the molecules in problem 1. So we had here that the carbon was in the middle attached to 4 fluorines. Excuse me. Yes, fluorines. And so that is going to look like this. Remember, this one goes back in the board, this one comes out towards you, and then these 2 are on the board. So that would give that to you. The next one, let's see, let's make this one in the plane with us. This one comes out towards us, and this one goes back in the board. The third one, so I was actually right in drawing it the way I did. It's a bent molecule. The fourth one, that's it. It's a linear molecule. And the last one is also a linear molecule. Okay? Number 3, so this would be A, B, C, D, E. I'm sorry I did them so out of order. C, D, E. You know what? Just to help, I'm going to put this one down here. Okay. Now we're trying to answer the question, which are polar covalent or purely covalent? To be purely covalent, it has to have either a tetrahedron with the same guy on all the outside edges, or it could be a linear molecule with the same guy on the outside edges. So this one is definitely purely covalent. This one is not. It is not a tetrahedron or a line, and so it is definitely polar covalent. This one is polar covalent because of its shape. It's not a line, it's not a tetrahedron. This is a line, but it's not the same guy on the outside edges, and they're not with the same electronegativity. Remember, that's the idea of the guy on the outside edges have to have the same electronegativity. And so these guys do, these guys don't. It's wrong shape, wrong shape. These have the same electronegativities and they're linear, so they would all, that would be purely covalent. So A and D are purely covalent, and B and C and E are polar covalent. And with that in mind, this would not dissolve in water, this would not dissolve in water, but these would dissolve in water because they are polar covalent. Name the following molecules. Okay, we're going to name these. First, remember, if it's ionic, you're just going to name the first thing and the last thing, and end the last one with an "ide" because it's a negative ion. If it's two nonmetals, then you're going to have to name it the way you name covalent compounds. So calcium is over here on the left side. It's a metal, so this would be calcium chloride. Not chlorine, it's chloride. This one is two nonmetals, nitrogen and oxygen, are over there on the far side of the chart. So this would be dinitrogen monoxide. Dinitrogen monoxide, because there's one of these. This is sulfur, which is over there, and oxygen, both nonmetals. So this is, you don't have to say monosulfur if it's the first one. So that's sulfur trioxide. Sulfur trioxide. This, both nonmetals, just like this one. So this is dinitrogen tetraoxide. Dinitrogen tetraoxide. And carbon and chlorine are both nonmetals. So this would be dicarbon dichloride. Number 6, order the following atoms in terms of increasing size. And we have okay, well, here's calcium. Oxygen is over here. Aluminum's here. And cesium is here. Remember that the size increases this way and this way. And we are supposed to be putting these in increasing size. It increases this way and this way. So the guy farthest over in this direction is oxygen, and then we have aluminum, and then we have calcium and cesium. Calcium and cesium. So that would be ordering them in increasing size, because remember the size increases this way and this way. And then number 7, order the following in terms of increasing electronegativity. Electronegativity increases this way and this way across the chart. And with that in mind, we're dealing with so once again, we have calcium in here, we have oxygen in here, we have rubidium. Got to find rubidium. There it is. Ga. Gallium 31. Here it is. All right, so we have phosphorus, oxygen, gallium, rubidium. And so if we are looking for increasing electronegativity, then it's going to be from here going this way. So it's going to be rubidium, and then it's going to be calcium, and then it's going to be gallium, and then we get to phosphorus and oxygen. So we're just increasing electronegativity this way and this way across the chart. And so that's where you come up with that. Number 8. Which of the following molecules will have one or more purely covalent bonds? Have one or more purely covalent bonds. Okay, well, we know that this is a purely covalent compound, but it's not purely covalent bonds because fluorine is the most electronegative thing in creation, and therefore those are definitely pulling harder. O2 has the same guy on both outside edges, so that's purely covalent, and that bond is actually shared equally. Whereas this one is definitely, let's see, the chlorine is not quite as high, so probably the oxygen is more electronegative, but one way or another, those are not purely covalent bonds. So the only one in those 3 that has purely covalent bonds is O2, because O2 is the same guy, so they pull equally. All right, go ahead and finish studying this and take your test, read the first half of the next chapter, and have a very blessed week.